Hello, and welcome to our RAD in Action webinar on building connected apps with Bluetooth and app tethering. My name is Al Mannarino, and I'm one of the Embarcadero software consultants. On this webinar, we'll discuss and demonstrate how app tethering and Bluetooth can be used to create exciting and new Internet of Things solutions with distributed connected apps. We want to look at this new connected world of technology to build new experiences for the Internet of Things. Here's our agenda. We'll give an overview on what is the Internet of Things. Then we'll show you how to use the new Bluetooth LE component in RAD Studio XE7 to capture data from Bluetooth LE devices and gadgets. For examples, we'll look at getting data from heart rate monitors and temperature, humidity, and accelerometer sensors. Next, we'll describe what is app tethering and how can you use app tethering components to build connected apps to add to a distributed Internet of Things solution. Lastly, we'll discuss what is the data lifecycle of an Internet of Things solution to allow us to better understand the possible data management and application logic tiers, and we'll leave some time at the end for any questions you might have. So, what is the Internet of Things? Well, there are many definitions on what is the Internet of Things. Wikipedia tells us this, that the Internet of Things is the interconnection of uniquely identifiable embedded computing devices within the existing Internet infrastructure. So what does this really mean? The Internet of Things means that the way we experience and interact with devices is changing. RAD Studio lets you breathe new life into your existing applications by enabling us developers to easily connect our apps to gadgets, devices, sensors, enterprise data, and cloud services. With RAD Studio, you can build complete Internet of Things solutions that deliver innovative user experiences. And you can easily deploy your Internet of Things enabled apps to Android, iOS, Windows, Mac OS X natively with a single C++ or Object Pascal codebase. And that's very exciting. We can now extend our existing apps to gadgets and wearables. And we see it every day. More and more gadgets and devices are being added to the Internet of Things ecosystem every day. The interconnection between these gadgets and devices has the potential to create remarkable new user experiences. And RAD Studio lets us harness the power of Internet of Things solutions so you can add new capabilities to your existing desktop and mobile apps by integrating devices, sensors, enterprise data, and cloud services. And with the Internet of Things, you'll want to be able to extend your existing Windows and FireMonkey desktop and mobile apps to be able to integrate into the Internet of Things. And for that, you can use app tethering. Now, I'm going to get deeper into app tethering later into this presentation, but basically the app tethering technology in RAD Studio XE7 lets you easily distribute an existing app user experience across devices and gadgets. And this is especially powerful for extending the utility of existing desktop and mobile apps to integrate Internet of Things. So virtually all industries can immediately benefit, such as point of sales, food services, healthcare, manufacturing, and shipping. But the applications are limitless. And the building of these IoT solutions requires data to flow between devices, gadgets, the connected app, and the Internet by using Bluetooth, network Wi-Fi, and/or REST. And RAD Studio streamlines this application development by providing a easy-to-use component-based solution for Bluetooth, Wi-Fi, REST, and backend as a service communication protocols. One example of an Internet of Things solution could be a connected medical office. Now, IoT has many great applications in the medical industry. And by adding Wi-Fi and Bluetooth connected medical gadgets to a doctor's office, the medical staff can quickly retrieve and update patient data around their weight, blood pressure, and heart rate, and even perform long-term studies on sleep patterns to help patients with sleep issues such as insomnia. Now, the data received from these gadgets can then be stored in an encrypted database, and then you can analyze the historical patient data over time. And by adding beacons for location-aware apps, the medical staff can automatically check in patients as they arrive into the clinic, or notify them on their mobile devices that it's time to update their insurance record or that a copay is due. Let's now look at the new RAD Studio XE7 Bluetooth LE component. Both C++ and Object Pascal has a new runtime library API for Bluetooth LE low energy, also called Bluetooth Smart. The runtime library has a new unit called system.bluetooth, and it provides a multi-device API to access the Bluetooth features of the device that is running your application. This new unit provides support for both classic Bluetooth and Bluetooth Low Energy. Now, the component has these properties and these events that we see on this slide. And in a few moments, we'll take a look at an application and see how to use these properties and events. So basically, you'll drop the Bluetooth LE component onto the form. Then we can call its Discover Devices method. And for example, with this syntax, we can scan for 2.5 seconds, looking for any devices and or gadgets that are heart rate service. Then all of the Bluetooth LE devices, sensors, and or gadgets within range will get discovered, and then we can select the one we want to use. Then we can get all of the services, characteristics, and descriptors of the device, sensor, or the gadget. For Bluetooth LE, we follow the GATT specifications, generic attribute profile, and we use the Bluetooth profiles and services based on GATT that you can get from the developer Bluetooth website. So for example, if we wanted to work with a heart rate service from the Bluetooth website, we find that the heart rate service has an assigned number of 0180D. So to get the service you need, you use the complete UUID, which is the assigned number for the standard service, plus the base Bluetooth code. So for example, the complete code for our heart rate service is this code we see here on this slide. So now once you have the heart rate service device, we can get its characteristics, such as the heart rate measurements and body sensor location. And like we see here, for our heart rate monitor, the body sensor location can be one of 7 locations, such as your chest or your finger, your earlobe, or your foot. So then we can use this array of body sensor locations to get the location of our device. And I'm also happy to tell you that you can also work with devices and sensors that are non-standard GATT profiles. So for devices and sensors with non-standard profiles, you can create server and client applications using the same Bluetooth LE technology without using GATT profiles. And that means you can create your own services and characteristics for a private communication between server and client devices. Let's now look at how we can use the new RAD Studio XE7 Bluetooth LE component to capture heart rate beats per minute from a Bluetooth LE heart rate monitor. So for this example, I'm going to be using a Zephyr smart heart rate monitor, but any Bluetooth LE gadget, device, or sensor that has a Bluetooth LE heart rate service should also work. So for this app, to build it as a connected app and create a distributed Internet of Things solution, we have a client application to collect the heart rate beats per minute data and also graph the historical beats per minute data on another tab. We added a backend as a service cloud service to handle authentication and database services to store the data. And then we added a separate medical administration app that gets push notifications whenever a patient's heart rate beats per minute exceeds their recommended threshold, so the responsible medical team can immediately take the necessary medical action for the patient. So now this scenario, it can be used in hospitals, clinics, and even be used in fitness centers. So with these types of personal heart rate monitors, you can now work out smarter in your gyms or your fitness centers. Physiologists and fitness trainers recommend working out within certain heart rate zones to achieve goals such as weight loss or cardiovascular improvement. You no longer have to hold on to those dirty handlebars on treadmills in a gym, because these new Bluetooth LE heart rate monitors continuously monitors you for faster feedback. So now let's take a look at the app inside of RAD Studio and see how we added Bluetooth LE with backend as a service for push notifications to these applications. So here is RAD Studio XE7 with the heart rate monitor and remote push notification apps. We have these apps in both Object Pascal and C++. Here we're going to be using the Object Pascal version. So let me quickly explain what these apps do, then I'll run the apps, and then we'll come back into the IDE and we'll walk through the code and see how they were created. So we have two projects here. Project 1 is the heart rate monitor, and project 2 is the remote push notification project. So for the heart rate monitor, we have two forms. One is the login form and the other is the heart rate form. So from the login form, we allow the user to log in against a predefined backend as a service user account. And once they log in, we have a second tab that will let them set their threshold based on what their doctor or their personal trainer recommends it should be. And if your heart rate exceeds that threshold, then a push notification is going to be sent to this other remote push notification app, so your medical and or your training professional knows the name of the user and their current heart rate. On the login form for the backend as a service provider, for our user authentication and to store our heart rate data, we're using a KinV provider component, a backend storage component, and a backend users component. After logging in and setting the heart rate threshold, we then display the heart rate form to show our heart rate beats per minute. Now on the heart rate form, we're using our Bluetooth LE component to get our heart rate from the heart rate monitor. For the backend as a service, we have our KinV provider, a backend query component, a backend storage component. Now we also have a REST response dataset adapter component, and we see it's bound to a FireDAC memory table, an FDMem table component as our dataset, and this gets the response JSON from the backend query component. And we have a backend push component with a push endpoint called myMessage that lets us use business logic in the cloud to send push notifications to the other separate administration app if we get a heart rate above the threshold. On another tab that we call the History tab, we added a chart. And here we're using the T-chart component to graphically display the heart rate recorded data. And lastly, on the Settings tab, we display the Bluetooth heart rate monitor information. We get the name of the heart rate monitor, the sensor connection information, with body location of the heart rate sensor and if the heart rate monitor is connected for its contact status. The second project that we call Remote Push, this is our Heart Rate Cloud Administrator application. It has just one form, and it's designed for the medical professional or the health club trainer. So this is the app that's going to receive the push notifications for the users that have heart rates above the threshold that we set on the heart rate application. So it has two components. It has the same Kinvey provided component with the same settings that we set on the heart rate monitor app, and we also added a push events component, and it has the same push event property called My Message that we defined inside our Kinvey backend as a service backend. Let's now deploy and run these apps and see what they do. Now these are multi-device applications, so we have our choice to deploy them to either iOS, Android, Mac OS X, and or Windows. So for my heart rate monitor, I'm going to choose to deploy it to an iOS device. It'll be an iOS 8.1 to an iPad. And for our admin push notification app, I'm going to choose to deploy that to Android, and Android Nexus 7 tablet. So let me now build and deploy these two apps, and we'll see what they look like. So here we see the two apps running on the devices. The heart rate monitor is running on this iOS iPad, and the heart rate cloud administrator is running on an Android Nexus 7 tablet. And I'm wearing my Zephyr heart rate monitor on my chest. So now I'm going to log in as myself. It now does the authentication to the cloud, and that worked great. Now I need to set my beats per minute notification threshold. Now a healthy resting heart rate is somewhere between 60 and 100 beats per minute. Now a highly conditioned athlete, they often have resting heart rates somewhere between 40 and 60 beats per minute. But I'm not one of them, so I'm going to set my threshold to be about 100. So now I can push the scan button, and now it waits about 4 seconds looking for all the Bluetooth LE devices, and once it finds my heart rate monitor, it will connect to it, and then we should start receiving data from it, and we should see my heartbeat beats per minute. So right now I'm at a nice comfortable 99. So let me stand up and do some running in place to try to get it past 100. And we did. So now it's past 100, so it immediately sent the push notifications to the Heart Rate Cloud Administrator app, letting either my medical folks and or my personal trainer in my gym know that my heart rate is higher than it should be, so they can now take the necessary corrective actions. And on the heart rate monitor, we have separate tabs on the bottom, one for history. So if I look at the history tab, it's going to display my historical beats per minute on a graph. So we see that. And I also added that memo box on the bottom to display heart rate, Bluetooth LE data. So you can see all the UUIDs for the heart rate measurement, body sensor location. So all of the descriptors and all of the characteristics are displayed on that memo box. And the last tab, the settings, here's where we can get information on the heart rate monitor. So if I wanted to know, for example, what type of heart rate monitor I'm connected to, in my case it's my Zephyr heart rate meter, I get sensor connection information. So sensor location, it knows I'm wearing it on my chest, and sensor contact has been detected. So all of that is working great. So now let's go back into the IDE, and I'll walk you through the code, and we'll see how we created these apps. We do have a detailed write-up on how we created these apps. including setting up the backend as a service using Kinvey and setting up the cloud and messaging services for the push notifications. So you'll be able to read the white papers for all of the details. Looking at the heart rate monitor project, it consists of two forms, the login form and the heart rate form. On the login form, this allows the user to log in against a predefined backend as a service user account that we created using Kinvey. On Kinvey, I created a new app called My Backend as a Service app, and in that app, I created my users. So Al was the username I used to log into our heart rate monitor, and we used the backend as a service to authenticate the username and the password. After we log in, we go to the threshold tab where we can set our beats per minute notification threshold based on what our doctor or our personal trainer tells us. And then when our heart rate exceeds that threshold, then a push notification gets sent to the Heart Rate Cloud Administration app, letting them know the name of the user and their current heart rate. To enable the backend as a service, we have a Kinvey provider component, a backend storage component, and a backend users component. Now both the backend users component and the backend storage component are connected to the Kinvey provider as their provider property. On the Kinvey provider component, from the Kinvey app we created, we set the app key, the app secret key, and the master secret. And we have a username and a password. We will use this username and password to be the same one assigned to the app that's going to receive the push notifications. So this will either be the admin or the medical professional who's going to receive our beats per minute if we exceed the threshold. Looking at the on-click event for the set button, here we see we create a new JSON object, and we are adding two new JSON pairs. One for the threshold from the number box and the username from the login screen. And then we create a new JSON object that contains both of those JSON pairs, and then we create a new data collection that we're calling heart rate user data on the backend as a service using Kinvey. Now the collection is going to have two columns, one called threshold and the other one called username. And it's going to store the threshold value we entered in the number box and the username from the login. And then we display that the threshold gets set, and then we hide the login form, and then we display the heart rate monitor form. Now if we look at our Kinvey account, under data, we see our data collection that we created, heart rate user data, and it has the username and the threshold that we set. Looking at the heart rate form, this is our main application. It also has a Kinvey provider component with the same property set as the login form. It has a backend storage component for storing all the new heart rate data we'll be receiving from the heart rate monitor. We have a backend query component that will look at my Kinvey backend using this new heart rate cloud data collection that's going to get created in Kinvey when I scan for my heart rate. And as soon as I scan for the heart rate and get a beats per minute, then we're going to write to this new data collection that we're going to call heart rate cloud, and we'll store the current heart rate and the time for that heart rate in the data collection. Now this backend query component is able to retrieve that stored data in the cloud. On the History tab, we have a list view that is bound to the backend query component to display the historical data. Now, if we look at Visual Live Bindings, we see that we have visually bound the list view to the beats per minute log and to its text property, and the time to the detail property on the list view. And these are going to be the two JSON pairs that we're going to create. And on this History tab, we also added a chart using the included T-chart components to graphically display the recorded data. And on the Settings tab, here's where we can display the Bluetooth heart rate monitor information. We're going to get the name of the heart rate monitor, the sensor connection info with the body location of the heart rate sensor, and if the heart rate monitor is connected for its contact status. And last, and just as important, we're going to be using our Bluetooth LE component with this application. Looking into the code, one of the first things we needed to do for this Bluetooth LE app was to get the Bluetooth UUID for a heart rate service. So from the Bluetooth website, under Home, GAT Specifications, Services, Service Viewer, we're able to find the service that exposes heart rate and other data from a heart rate sensor. And that service exposes the heart rate monitor's beats per minute and other data. And the heart rate sensor is using one of the standard Bluetooth GAT profiles. The next thing we did, and again, from the Bluetooth website under GAT Specifications Characteristics, was to get the heart rate measurement characteristics and body sensor location UUIDs. And the body sensor location characteristic value is used to index this array to display the string of where the user is wearing the heart rate monitor. On the heart rate form, when we click on the scan button, we perform do scan, and here we call the Bluetooth LE discover devices method. We scan for 2.5 seconds looking for heart rate service devices. At the end of this 2.5 second timeout scanning looking for devices from the Bluetooth LE component, then the on and discover devices events gets fired, and here we get the list of all discovered Bluetooth LE heart rate service devices that we found. Next, we can get the service and characteristics from our devices. And here we can find and list of all the available services and characteristics, and we can search for specific ones, such as heart rate and monitor position. Then we can subscribe to the characteristics, and we can do that by calling the Bluetooth LE component its method called subscribe to characteristic. And once we start receiving data from the device, the on characteristic read event gets fired, and here we can start collecting data and display it on our user interface. Now, to manage the characteristic data, we have a method called manage characteristic data. And here we could check to see if the characteristic is a heart rate measurement beats per minute, and if it is, we have a method called display heart rate measurement data, where we can take the beats per minute data and display it on the label on our heart rate monitor app. To save our data to the cloud, we added a new method called save in background. And what this method does is it's using threading to execute and store the continuous heart rate data in the cloud while you are processing the data. So here we're also using the new parallel programming library for background processing to store the data as it's being retrieved. So this way, with multiple threads and the parallel programming library, we can continue to use the user interface as data is being stored in the background. So that's great. In this method, we create a few variables so we can record the heart rate with the timestamp, and then we add several JSON pairs for the beats per minute log, and that's our current heart rate, the current time, and the last one for the username, and that's the username we get from the login form. So we create several JSON pairs in this save in background method, and again we're using the new parallel programming library task method, and here we're going to create a brand new data collection called heart rate cloud in our Kinvey backend service, and it's going to have the three columns: the BPM log, time, and the username, and this all uses the backend storage component, so that's also great. Looking into our Kinvey account for our My Backend as a Service app, we have our two data collections, one called Heart Rate Cloud and the other one called Heart Rate User Data. For the Heart Rate Cloud data collection, we have our three items: beats per minute log, the timestamp, and our username. And if these two data collections don't exist, they get created for us once we run the app. On the Measure tab, we use this label to display our heart rate beats per minute, and we have a list view that displays our heart rate data. And here in code is where we display the current heart rate on the label and add the heart rate data to the list view. And if our heart rate data exceeds our threshold, then we send a push notification using the backend push component. We send a title and a message. The backend push component also uses the Kinvey provider as its provider, and the Kinvey provider on this heart rate form has a push endpoint property called My Message. Now this lets us use business logic that lives in the cloud on Kinvey that uses JavaScript to let us send push notifications if we get a heart rate above the threshold. So it's a push trigger that we can execute anytime your heart rate exceeds the threshold. On the Kinvey account, here's the JavaScript we added to My Message to send the push notifications. The form also has a timer component, and if we look at the onTimer event, it says that if our active tab is the history tab, then we update the graph every second, so you will see continuous data on the graph in the history tab as we are retrieving data from the heart rate monitor. The last component we want to look at is this REST response dataset adapter that's bound to a FireDAC FD table. Now the FD table is connected to the REST response dataset adapter. If we look at the properties of the FD table, we see that we're using the FD table as a dataset from the dataset property of the REST response dataset adapter, and the response JSON is set to the backend query component. We then store the data we get from the cloud in our FD table, and we are able to bind it to our list view to be able to display data from the cloud and display the historical data in the list view also. And if we look at the Live Bindings Designer, we see that our FD table is bound to our list view, so we can display the beats per minute and the time. So that's great. Next, let's quickly look at the remote push application. So this is our Heart Rate Cloud admin application. So it's been designed to be used by the medical staff or your fitness trainer to monitor your heart rate. So this app receives the push notification that the admin will receive once the heart rate exceeds the predefined beats per minute threshold that we set on the heart rate form for a specific user. Now, to be able to send the push notification to the medical staff, we have two components. We have the Kinvey provider component with the same settings that we defined on the heart rate monitor project, and we have our push endpoint property with our My Message on this Kinvey provider, and that's needed in both the heart rate app and this remote push app. And then we saw on the Kinvey account, on the business logic, we saw the JavaScript code that we added for the push notifications. And lastly, we have a push events component that also gets linked to our Kinvey provider. and we defined an event called onPushReceived. And for this event, we're going to add text to our list view items, and we will show the name of the user plus their current heart rate, and we send this notification to the medical staff. So that was a quick code walkthrough on how we added Bluetooth LE, back-end as a service, and push notifications to these applications. Let's look at another example of using this Bluetooth LE component, because with the proliferation of devices, gadgets, wearables, and the Internet of Things, we as developers, we need to learn how to connect our existing and new multi-device applications to Bluetooth low energy devices. So let's look at how to get temperature, humidity, and accelerometer data from a Bluetooth LE device. So for this example, I'm going to be using this Texas Instruments CC2541 microcontroller. It's a power optimized true system on a chip solution for both Bluetooth low energy and proprietary 2.4 gigahertz applications. And only for about $25 US, you can purchase from Texas Instruments their Simple Link sensor tag that has the microcontroller with 6 different sensors. So you can use this for temperature, humidity, pressure, accelerometer, gyroscope, and a magnetometer. So for this demonstration, I'm going to show you how to get data from the temperature, humidity, and accelerometer sensors. So here's the app running on an iOS device. Now when the Bluetooth LE device is on, it starts to advertise the services it offers. So if I click on the Find Devices button, it will scan for a few seconds looking for Bluetooth LE devices, and if it finds our sensor tag, like it did right here, I can select it, and then I can click Subscribe to Data. Now, when I click Subscribe to Data, this tells the device that we are ready to receive all the data that we are requesting. So for this example, we are looking for the ambient and target temperature, the humidity, and any accelerometer data. So for example, we could use the accelerometer data to let us know if the patient is moving inside of the room. So similar as we did with the heart rate monitor, if we wanted to monitor the patient's high temperature, we could check to see if the target temperature is above normal body temperature. So let's say between 36.5 degrees Celsius to 37.2 degrees Celsius for a healthy adult. Here's the app in RAD Studio XE7, and looking at the code, we see we are using the Bluetooth LE component that does all the work for us. It has great methods for discovering devices and their services and characteristics. You can read and write data from the characteristics using this Bluetooth LE component and subscribe to the data. It has these great events that we can use. So for example, the on-end discover devices event. When we call our discovered devices with a timeout, at the end of the timeout, this on-end discovered devices event gets fired, and we get a list of discovered Bluetooth devices. And then usually the next event after the on-end discovered devices is to call the on-end discover services, and that will give us a list of services for the device that we selected. The on characteristics read event gets fired each time a device is sent to us, and the on characteristic read request event is when we are implementing a GATT service. Same with the characteristic write and characteristic write request. When we click on the Find Devices button, we start the discovery process by calling the Bluetooth LE Discover Devices method. We scan, in this case for 4 seconds, looking for Bluetooth devices. And at the end of this 4 seconds, then the on-end Discover Devices event gets fired. And on the on-end Discover Devices event, here we are storing the name of the device that we want to discover. So in our case, we want to find a device named sensor tag. And when we read from its documentation, the device name can be a different name on different operating systems. So once we have the sensor tag, we add it to our list box. We select the sensor tag from the list box, and then we click on Subscribe to Data. And here's where we call the Bluetooth LE Discover Services method with the current device that we just selected. This causes the On End Discover Services event to be fired. And here is where we scan for all the services that we find. And if the services are the ones we want, like the temperature service, humidity service, and the accelerometer service, we can get their data. Now, looking at the documentation for the sensor tag, we do some operations in order to receive the data. So for example, for the temperature service, the documentation says we need to find this characteristic called UUID-IRT-CONF. And once we find it, we set the value of the characteristic to 1, and then we can call the Bluetooth LE write characteristic method to write this value to the device. And that tells the device to start sending the data of the temperature service, both the ambient and the target temperature. We do the same operations for the humidity service and for the accelerometer service. So we scan the services, searching for services by its UUID name. And then from its documentation, we need to find the characteristics. So for example, for the accelerometer service, we need to find its characteristic. And then we set its characteristic value to 1. And then we write this value to the device by calling the write characteristic method of the Bluetooth LE component. And this makes the device, our sensor tag, start sending data to us. And then the On Characteristic Read event gets fired. And here is where we can filter the data and translate the values that the device is sending to us. Reading the documentation on the sensor tag, we can see how we can translate the data into the real data that we will be displaying on the user interface. So for example, to get the ambient temperature, we can see the calculation here. So we do the same for the humidity and the accelerometer. And that's how you can use RAD Studio XE7 and the new Bluetooth LE component to get temperature, humidity, and accelerometer data from a Bluetooth LE sensor. App Tethering for building connected apps. Let's now look at App Tethering and see how you can use the App Tethering components in XE7 to build connected apps to add to a distributed Internet of Things solution. So the App Tethering technology lets us easily distribute an existing app user experience across devices and gadgets. And this is especially powerful for extending the utility of existing desktop and mobile apps to integrate with the Internet of Things. And for this, you can either use network Wi-Fi or Bluetooth Classic with App Tethering. Let me quickly introduce two new XE7 App Tethering features. The first one is App Tethering supports connections outside your subnet. So App Tethering was first introduced in RAD Studio XE6, both in CBuilder and Delphi. And App Tethering created a lot of excitement for both CBuilder and Delphi developers. All developers we spoke with loved the idea of App Tethering, but some could not use it in XE6 because their Wi-Fi is on a separate subnet from their wide area network. Most companies have the same scenario, where many times your Wi-Fi is on one subnet and your desktop app is running on a different subnet. So your companion app could not discover the tethering manager on your VCL or FireMonkey desktop computer. So this is an important enhancement needed for enterprise customers for their enterprise applications. To resolve this limit, the XE7 App Tethering functionality has been enhanced with App Tethering supports connections outside your subnet. So in XE7, both of these methods, Auto Connect and Discover Managers, provides an optional target parameter that you can use to override the default behavior of looking for devices in the same subnet of the local area network. So now with XE7, you can specify a target IP address or a subnet to search for remote managers. For example, as we see on this slide, to specify an IP address to search for remote managers, you specify that IP address as the target. So here we have this IP address as our specific target. Or to specify a subnet of IP addresses, you specify an IP address with 0 as its fourth number. So for example, here we specify the IP address like this with 0 at the end. So in this case, your manager searches the 192.168.1 subnet for remote managers. Now I'm also going to mention that you cannot specify wider subnets. So for example, I could not have 192.168.0.0. So that's not supported. So now either of these methods, auto connect or discover managers, they can be used to app tether to remote managers. The auto connect method, that's good to use as a quick way to connect with all willing remote managers. And the discover managers method, that's the method to use if your app needs greater control over which remote managers to pair with. The second new feature is adding support for Bluetooth Classic tethering in addition to network Wi-Fi based tethering that we had in XE6. So now in XE7, app tethering works with either Wi-Fi network or Bluetooth Classic, and this opens us to many different types of new apps to create. The runtime library has a new unit called system.bluetooth that provides a multi-device API to access the Bluetooth features of the device that is running your application. This new unit provides support for both classic Bluetooth and Bluetooth Low Energy. So you can now use app tethering to connect your application using Bluetooth Classic in addition to IP connections. Now it's important to note here that is in XE6, if you used network Wi-Fi based application tethering, you can easily switch your existing apps to use Bluetooth Classic tethering in XE7. Like we see on the slide, the only change you need to make is to switch the allowed adapters property from network to be Bluetooth on your tethering manager component. You will also need to make this change to the tethering manager component on all the other tethered apps. For those of you that are new to app tethering, let me quickly go over these two app tethering components, the tethering manager and the tethering app profile. Now these components follow the Bluetooth profile model. So there's a main component and then a profile that implements the functionality. The tethering manager is the component that manages all basic operations such as auto discovering and pairing with other remote managers. The tethering app profile implements the application profile. It's a set of functionality that includes executing remote actions, sharing resources, and sending streams and strings between other paired profiles. A manager needs to register a profile to start, so you need to drop both a tethering manager and a tethering app profile component onto your form and then link both components, filling in the manager property in the tethering app profile component. To find other tether applications in the network, you need to execute the methods either auto connect or discover managers. Now using auto connect, this starts the automatic connection to remote managers on each registered adapter. Using discover managers, this starts the discovery of remote managers on each registered adapter. Now for both the auto connect and discover managers, for communications over the network, an automatic timeout is 1.9 seconds. And for communications over Bluetooth Classic, the automatic timeout depends on the number of paired devices to the manager. On either method, you can set a timeout. And when the timeout finishes, you receive either the on-end auto connect or the on-end manager's discovery event, in which you receive a list of the discovered remote managers. And then from this list of remote managers, you can choose the ones you want to pair with. So now let's take a look at some RAD Studio XE7 examples on how to use app tethering for your VCL or FireMonkey apps using either Wi-Fi or Bluetooth Classic. So here's our Bluetooth LE with App Tethering app. So for this example, we took the RAD Studio XE7 Bluetooth LE heart rate monitor app and we added App Tethering. And with App Tethering, we created these companion apps that we're calling our heart rate monitor data receiver apps. Using the App Tethering Profiles Resource Updates or temporary resources, we can send the heart rate beats per minute from the heart rate monitor to the companion apps. So for example, patients in a medical clinic or people in a health club can be wearing a heart rate monitor, and then other medical staff or your health club trainer can be carrying the heart rate monitor data receiver app, and that allows them to remotely monitor your heart rate. So now let me run these apps first, and then we'll look into RAD Studio XE7 and see how we added App Tethering. Here are the apps running. So these are FireMonkey multi-device apps. So they could be running on Windows, Mac OS X, iOS, or Android. First, we see on the App Tethering logs that we can get a unique GUID local identifier for each of the apps. So by doing so, we can uniquely identify each app that is part of App Tethering. I started the Bluetooth heart rate monitor app, and then I started two companion heart rate monitor data receiver apps. Now the Tethering Manager's discovery method will look for other remote managers to pair with. So from the logs, we see that our heart rate monitor app did find our two remote managers to be able to pair with. So when I click on the scan button of my heart rate monitor app, it scans for my heart rate sensor, and once it finds it, it starts collecting my heart rate beats per minute. And then from here, using App Tethering, these companion apps connect to the heart rate monitor, and the heart rate monitor sends its heart rate beats per minute data to the heart rate data receiver apps. So all of this works great. Now let's look into RAD Studio XE7 and see how we added App Tethering to these apps. First, let's look at the Bluetooth heart rate monitor form. Here we added both the Tethering Manager and the Tethering App Profile components. For the Tethering Manager's properties, we added a password and we gave it a unique text name to distinguish this manager from any other manager. So for these apps, we're going to use both the password and the unique name of this heart rate monitor app to allow other remote managers to be able to pair with us. And for allowed adapters, here's where we can switch between network and Bluetooth tethering. For these apps, we're going to use network. For the Tethering App Profiles properties, we set the Manager property to be the Tethering Manager. For resources, we added a resource called My Beats Per Minute, and we're going to use this resource to save and send the heart rate data to the other connected apps. And we also gave the Tethering App Profile a unique text name to distinguish it from other profiles. For the Tethering Manager events, we are using mostly all of the events. So for the on-end manager's discovery event, this gets triggered when all remote managers have been discovered following a call to discover managers. And here is where we check if the remote manager's text matches the local manager. So we check if the text property matches that of our heart rate monitor manager's app. And if it does match, then we can pair with it. The next event, on-end profiles discovery, this gets triggered when all remote profiles have been discovered, and it has a parameter called remote profiles, which is a collection of information on all discovered remote profiles. The next event, on new manager, this event fires when a new remote manager pairs with others on a tether. The next event, on paired from local, so this event gets triggered when a remote manager pairs with your local manager. The next event, on paired to remote, so this event fires when your local manager successfully pairs with a remote manager. The next event, on remote manager shutdown, This event triggers when a paired remote manager disconnects. The next event, on request manager password. So this triggers when your local manager requests to pair with a remote manager, and that remote manager requires a password. This next event, on request storage, we're not using this event, but it would get triggered when a remote manager checks to see if information can be stored on your local manager. And for this last event, on unpair manager, this event triggers when a remote manager unpairs with your local manager. So it has a parameter called manager info, and it contains information about the remote manager that unpaired with us. Now there is another event called on end auto connect, and this would get triggered if we use the auto connect method at the end of its timeout. But in these apps, we're using the discover manager method instead of the auto connect method. And these last two events, the on auth error from local and the on auth error from remote, these would get triggered when a remote manager or when a local manager attempts to pair and the passwords don't match. For the Tethering app profiles events, we are using these events. So we have an event called on resource received, and this gets triggered when a remote resource is received from a remote profile. So it has an A resource parameter that contains the actual resource. And this is the event that we're going to use to send our heart rate beats per minute as temporary resources to the app tethered paired apps. Now there's another event called on resource updated. And this is the other event that we can use to send heart rate beats per minute to the other app. So this event fires when a resource, our beats per minute, has been updated in a remote profile. So it also has the A resource parameter, and it's the actual updated resource. And this applies only to persistent resources defined within a remote profile. The last event we're using is the on disconnect, and this event gets triggered when your tethering profile disconnects from a remote profile. So it has a parameter called a profile info that contains information about the profile from which your application has just disconnected. Quickly looking at the other companion app, our heart rate monitor data receiver app, we add both the tethering manager component and the tethering app profile component. For both components, we add a unique text name to uniquely identify both the tethering manager and the tethering app profile. The tethering manager component also has its password property set. On the tethering manager component, the allowed adapters property is also set to use network. And for events, for both the tethering manager and for the tethering app profile, we are using the same events with the same code as we did for the heart rate form. And that's important to note because app tethering does not form a distinction between a client and a server. App tethering is a peer-to-peer connection between two or more applications or application instances on the same machine and or across a network. So app tethering acts as both a client and a server. On the heart rate form, to start scanning for remote managers to pair with, we added the tethering manager discover managers method on the form's on create event like this. And on the companion heart rate monitor data receiver app, we added this scan for heart rate monitor app button, and it calls its tethering manager discover managers method to scan for remote managers to pair with. At the end of the discover managers event timeout, the on end managers discovery event gets fired, and here is where we can pair with the remote managers. Next, the on profiles discovery event fires, and here is where we can subscribe to the beats per minute resource. And on the heart rate monitor form, when the heart rate beats per minute value changes, we can call the tethering app profiles send string method to send the updated beats per minute resource to all of the connected tethered apps. That was a quick look on how you could add app tethering components to build connected apps to add to a distributed Internet of Things solution. And app tethering works great on and between Android, iOS, Mac OS X, and the Windows platform. And app tethering is very easy to set up and use, and it has great functionality and great events. And app tethering enables apps to automatically discover each other over a network, so it can exchange resources and execute actions or trigger methods within each other. For other app tethering examples, look at the samples provided in RAD Studio XE7. There's a database shopping list app that shows app tethering sharing resources between other paired profiles. There's a media player app that shows app tethering executing remote actions like play, stop, and volume control using remote control between other paired profiles. So there's a media player HD app that's multi-device, and there's a separate multi-device media player command app for remote control for the video player. There's a desktop cast app that shows sending screenshots and actions to other paired apps, and any of the apps can take live screenshots and then live cast the image to the other connected apps. And lastly, there's a photo wall app that shows app tethering sending streams between other paired profiles. The photo wall app has a desktop wall viewer app that's also a multi-device app to display photos taken with its mobile counterpart applications. The mobile app from the photo wall project lets you take a photo with either your Android or iOS device and display it on one or more of the desktop wall instances over the internet. And here are some examples from customers that built apps using the app tethering components. There's a mobile barcode scanner app tethers to desktop app, and this is mobile barcode scanning and processing via specific phone apps with barcode data forwarded to VCL warehouse management apps. There's a medical mobile imaging app for doctors with a VCL management app using a mobile phone or tablet to take pictures of patients' conditions and send the images to dedicated app tethered VCL apps. There's a remote device camera app, and this is for remoting device camera to desktop or different mobile device application. And there's also a nice chat room app that's a really nice example of being able to build a chat room using app tethering. And for Bluetooth examples, look at the sample apps in XE7 under Device Sensors and Services Bluetooth. And you'll see these 6 samples on using Bluetooth LE and Bluetooth Classic, including the heart rate monitor app that I used in this presentation. Bluetooth app tethering. So the last item I want to mention in this section is using Bluetooth Classic with app tethering. So the only change you need to make is to switch the allowed adapters property from network to Bluetooth on the tethering manager component. And you'll need to make this change to the tethering manager component on all tethered apps if you want them to use Bluetooth Classic instead of network. And before running the apps using Bluetooth Classic or even Bluetooth LE, is you need to ensure that both of your devices are paired. So in my example, I'm using a Google 2013 Nexus 7 tablet that I paired to my MacBook Pro. On my Nexus 7, I selected Settings and turned Bluetooth on. I then clicked on Bluetooth and selected to search for devices. Once the Nexus 7 found my MacBook Pro, I clicked on it to pair my Nexus 7 device to it. And then my Nexus 7 also appears in my list of Bluetooth devices on my MacBook Pro. In this last section, we'll discuss what is the data lifecycle of an Internet of Things solution to allow us to better understand the possible data management and application logic tiers. In the Internet of Things, the ability for newer, smarter devices to communicate with each other, with back-end data centers, and with related systems requires data to be processed into information in different ways and in more than one location and direction. As this figure illustrates, the Internet of Things pushes data processing to the edge. Our tactical data processing can occur at the controller tier with data analyzed near field to allow immediate action to be taken. And this is the data that we get from the devices, sensors, and gadgets. Next, this field level information analysis prompts actions based on predetermined business rules. And once these actions occur, summary information is relayed to the back office for deep analysis. RAD Studio has the Intrabase Database Developer Edition and the free Intrabase Lite IB Lite database that you can embed into your multi-device applications. And the Fast Reports reporting tool has a fast cube that lets you analyze data and to build summary tables, data slices, as well as create a variety of reports and graphs. So it's a very handy tool for the efficient analysis of data arrays. The knowledge we gain from that analysis determines how best to optimize the system and can result in new rules being set to improve process flow. This constant feedback loop between our tactical field operation data and strategic information analysis allows decisions to be made as close as possible to the edge of the network. This results in reduced data transmission costs and quicker decision-making in enterprise Internet of Things implementations. The Internet of Things can transform your data and your business. The Internet of Things information lifecycle can lead to transformed, efficient business processes, the innovation of intelligence, self-aware and customized product solutions, and better customer experiences. Not to mention new revenue streams, faster time to market, and higher profit margins. So how do you align solution architectures to the Internet of Things information lifecycle? Well, the Internet of Things is fundamentally reshaping business and technology requirements within the business landscape. Innovative solutions that intelligently monitor and control remote sensors and devices are revolutionizing enterprise computing. These next generation intelligent systems, some of which we see here with their logos, are collecting, analyzing, and enabling organizations to act upon massive volumes of raw business data generated by vast numbers of endpoints to improve business intelligence and automate business processes. So network and system architects will need to reorganize their IT infrastructures to accommodate and support the Internet of Things. And the good news for us RAD Studio developers is RAD Studio XE7 is the complete solution for building Internet of Things connected apps for Windows, Mac OS X, iOS, Android, gadgets, wearables, and sensors. So that's really cool. The last thing I want to talk about in this section is what the Internet of Things means for business app developers. Now, Embarcadero sponsored a recent global survey of over 1,000 active developers asking how the Internet of Things will affect business decisions for 2015. And the survey revealed this year, 2015, will be a big year for developing business solutions with integrated things, such as industrial sensors, drones, health monitors, and smart buildings. We see from this chart, the survey respondents had widely varied ideas about how they would communicate with their business things using network Wi-Fi, Bluetooth, REST APIs, and other SDKs. The good news is RAD Studio already has the capabilities to build and deploy these solutions. The survey also revealed the majority, 84% of software developers building Thing solutions in 2015 are targeting business markets, while only 16% are exclusively targeting consumers. So in the survey of 1,040 developers, 77% of the development teams will have Internet of Things solutions in active development in 2015, and almost half of Internet of Things developers anticipate their solutions will generate business impact by the end of 2015. The resulting survey report that you can download from this link focuses on 4 questions Internet of Things developers are facing today. How will the Internet of Things impact business? What forces are driving development decisions around Internet of Things solutions? What critical development skill sets will be important when implementing Internet of Things solutions? And how will Internet of Things solutions change the end user experience? This ends this webinar. To summarize, we looked at what is the Internet of Things and what does it mean for us application developers. We saw how you can use XE7 to capture Bluetooth data from devices, gadgets, wearables, and sensors. We saw how you can use App Tethering to build connected apps and create a distributed Internet of Things solution. And lastly, we looked at the data lifecycle of an Internet of Things solution to understand the possible data management and application logic tiers. The last item I want to mention is these are the current special offers and bonuses for RAD Studio XE7, Delphi XE7, and or C++ Builder XE7. You have buy XE7 now and get a free copy of the next major release. Buy one and get one free promotion. Free tools include the Interbase database, Rapid SQL, ER Studio, FireDAC, and other Embarcadero database tools. You can save up to 45% when upgrading from any previous version. If you upgrade from Professional Edition to XE7 Enterprise or higher, you will receive free 10 user deployment licenses for the Enterprise Mobility Services, EMS. And lastly, there's a free bonus pack valued at over $700 with the purchase of XE7. The pack includes Castalia for Delphi, the Meter Converter Basic for XE7 to help convert your VCL forms to multi-device forms, the new Object Pascal Handbook by Marco Cantu, and VCL and FireMonkey Premium styles. And you can visit embarcadero.com/RAD offer page for all of the details. Thank you all for attending this RAD in Action webinar. Let's now open up this session to any questions you might have. So this was fun for me doing, so it's real exciting, how you can use this app tethering technology and Bluetooth to create these really exciting and new Internet of Things solutions with these distributed and connected apps. So it's quite exciting what's possible today and what we can do as RAD Studio developers.
Yeah, and I just, you may have covered it, I'm not sure, because sometimes it's a little detail. If you're using network app tethering, and you do a discover, the technology does a UDP broadcast, right, over a range of ports?
That is correct. So the discovery is UDP, and to discover the devices, and then the sending of data or streams back and forth, that's done by TCP.
Right, and then it uses, it scans across ports 2020 to 2040. So I just wanted people to know that they need to open up, make sure those ports are open.
That's correct. If I started those app tethering apps live, you would see the friendly firewall warning message pop up telling you that you're about to go through firewalls and you'll need to give permission to do so.
Yep. And the other thing for me is whenever I think about building connected apps and app tethering, I think about all the different possibilities, and you showed that as well. If you've got a VCL app and another VCL app, you want to connect them together, you can use app tethering. It's not just for devices to desktops or servers. Any kind of target application that you would want to build, you can use these non-visual controls, whether it's a console app, a server app, a desktop app, a mobile app, and any combination of all of those. So If you've got a VCL app or two VCL apps, you want to connect them together, drop down, two tethering components, connect them up, and go.
That's correct. Yeah. That's correct. And there's a lot of common questions that come up with this. I see Danny posted a question about, is it possible to use the Bluetooth LE component to do beacon, iBeacon? Now, I know we have plans to add iBeacon support, and by iBeacons you get all that great location-aware apps. Now, I think, David, at one point you were working on some type of iBeacon type of application, and I think it was you who found out that iBeacons works differently on iOS and Android, and it's not in the Bluetooth LE component. It's exposed in other services. Yeah. So I know if you look at our roadmap, we do have the plans to add iBeacon support, maybe as a component. So just as easy as it is to use the Bluetooth LE component, you'll be able to drop a beacons component onto a form and have all its great properties and events. So maybe you can share some more on that, or what I said is probably all we can say.
Well, I did take a look, and what we want is a solution, component-based solution, so that you just would drop a beacon component down, and it would work on the different platforms that have APIs and SDKs for the beacon technology. And there's two different parts of that. One is Apple calls theirs iBeacon, and instead of it being in core Bluetooth, where we do the Bluetooth connectivity for things like OS 10 and iOS, I think it's in the advertising framework, because in a sense it's sort of for advertising or retail. I mean, that's some of the kind of applications I've seen people use. You go to a Lord and Taylor, not that I would go to a Lord and Taylor clothing shop, it's not me, but they've got beacons set around, so if you have the Lord and Taylor app and you walk down the aisle and you've got some preferences for things you're looking for, this beacon is constantly broadcasting. They either plug in or you can have battery power. It sends a specific payload. It has a UID, and then it has, I think it's bytes. Not sure the exact number of bytes. It might be two long words of major and minor number, and you use those numbers to identify something, like there's a special on jeans in that aisle, or tie-dye T-shirts in my case. And so iBeacon is what Apple calls their technology. There's also this Alt Beacon, which is sort of an alternative version. And I think beacons in Android is in the Bluetooth package, but it's different in different places. So what we're trying to do for the future is work on a component in RTL that will work across all the platforms. The other thing I wanted to mention about a RAD offer is there's an additional RAD offer since the time you grabbed the offers from the RAD offer page. This week, in fact, on Monday, I think it was. Today's the 25th. Is today the 25th? I think so.
I think even yesterday they added it.
We changed it. So for those who don't have XE7, if you upgrade between this week and the end of March to XE7, we'll give you the next version of whatever it is, Delphi, C++, Builder, RAD Studio. So
that's cool. I've been doing this. I've been going on the road a few times and talking to people about this App Tethering and Bluetooth, and I mentioned classic Bluetooth and Bluetooth LE kind of wrapped inside of that Bluetooth LE component. So sometimes that causes some confusion. How do I use classic Bluetooth with this Bluetooth LE component? But so it's not. So if you want to do anything with classic Bluetooth, it's not in the Bluetooth LE component. It's part of the new unit that we called system.bluetooth. So it supports both classic Bluetooth and Bluetooth LE or Smart. So there are classes in there like the Bluetooth server socket and the Bluetooth manager. So if you want to do anything with Bluetooth, then you would call you have the class Bluetooth manager, and you have Bluetooth adapter. So you would call Bluetooth manager. You would call its on discover end, and it would find a list of discovered devices or set of services that are classic Bluetooth. And then you can use the Bluetooth adapter class, and that allows you to pair with these classic Bluetooth devices. So if you look at the samples that we ship with, There are a couple of classic Bluetooth sample apps that we ship with that show you how to call the Bluetooth devices and or their services. So there's one using the a basic text server that classic Bluetooth supports, and there's another classic Bluetooth chat room app using the same technique. So it's kind of the same technique, same methods that are used inside of the Bluetooth LE component. But if you want to do it through classic Bluetooth, you just do it in the code by adding the system.bluetooth unit to your users clause.
And Danny just pointed out, Danny Wind is one of our MVPs, is out of the Netherlands, that there's another sample that ships for Bluetooth that's with the product XE7. It's a proximity example, and it uses what is commonly called a soft beacon type functionality or technology to create your Mac or whatever your Bluetooth device target might be, or sending machine. I use my Macintosh, for example, and I run it, and you turn it on, and it actually uses the Bluetooth capability on my Mac to broadcast out a signal. And then on the other side, I have a Bluetooth client application, for example, on my Nexus 7 tablet. And as I get closer, then it picks up the signal, and through the API and the runtime library, you can get an approximate distance. The way that works is there's the sending device, and you can see this in the proximity source code that we ship with XE7. The sending device will send out its signal through the hardware, and number two, it will pass along the power that it's telling the hardware to broadcast at. So what you'll get on the receiving side is you'll get the original power that was sent, that the sender told the hardware to send, a power level, and then what gets calculated is something called the RSSI, which is the relative signal strength indicator. And from the RSSI and knowing what the original sender was telling the hardware to broadcast power level, you can calculate an approximate distance. And I think in most beacon worlds, the simple beacon worlds for mobile, they have sort of this near, far, and so on. But there's a calculation, there's documents on the internet for calculating the number of feet or meters from an RSSI value. Again, that depends on some environmental factors. For example, if you're broadcasting through a wall that's got heavy steel in it, you're going to get signal degradation. The same thing with app tethering through Bluetooth. You mentioned a couple things, Al. One is you mentioned if you have the more paired devices you have for doing app tethering with Bluetooth, the longer it'll take to do discovery. But also
yeah, that's correct.
But also the signal strength, again, if you're broadcasting through either a long distance or through multiple walls and so on, depending on the material, you might also get a longer time, or you might not even find a device if it's too far. I think Bluetooth has, I think it's 100 meters max, something like that. Bluetooth LE is even shorter. I forget the sort of theoretical distance that a Bluetooth LE transmission takes, but it's not 100 meters. It might be something.
Yeah, that's correct. Anytime I'm doing anything with Bluetooth Classic, I have to give it a much longer timeout, like 10 seconds or 15 seconds, just to make sure it finds what it's looking for.
Yep.
So that reminds me of another question. There's these hundreds and thousands of Bluetooth devices and gadgets out there. How do you find the unique ID of these devices, like heart rate monitors? Well, if it's using these standard GATT profiles, the Bluetooth website, that's where you can get the UUID for the different services and different devices, as long as the manufacturer that created it is using a standard GATT profile. So we saw when I used that heart rate monitor example, we looked up the UUID for a heart rate service. For other devices like that sensor tag, we scanned for services, and in that case we found the devices by using its UUID name that we got from the documentation. And then we had to go back into the documentation to find what characteristic value to be looking for and for what service value to be looking for. So that that Discover Devices Proximity Sample app you mentioned, that's a great app to use. So in case you have any unknown Bluetooth device without any documentation, all you really got to do is make a few simple calls to get the device name, the characteristics, and the services. So when you do that, the Bluetooth LE Discover Devices, then you can filter on whatever you're looking for, and that's going to then return all of the Bluetooth LE devices that it found. And then at the end of that on and Discover Devices event gets fired, and that shows all of the found devices. And then once you have all the found devices, you run its Discover Services process, and that brings back all of its services. And then from there, you can get all of its individual characteristics. So all of that can be dumped out into a log file. So you can start from knowing nothing about some unknown Bluetooth device to finding a lot of information about it. So if you do have a Bluetooth device without any documentation, it's a nice way to be able to manage any standard Bluetooth LE device.
Yeah, the sample, there's a Pascal and a C++ samples Explore Devices LE. We give you the source code as well, and it'll go find what it can find. Around here, it finds several of the heart rate monitors. It also will find an Apple TV little box because that's got Bluetooth built in. And the other thing is that I put into the Q&A log the link on the Bluetooth.com site. The Bluetooth.org has a list of smart products that are, it's not a complete exhaustive list, but it shows you a lot of the sample products, stylus, height rate monitors, proximity sensors, body weight scales, heart rate monitors, breathalyzer I see on the list, thermometer, and some USB dongles and other things, smartwatch and so on, the Casio G-Shock smartwatch. The way to look at if you're thinking about purchasing devices or telling your customers looking for Bluetooth LE devices is if they have the Bluetooth Smart logo on the box and on the product. It's the Bluetooth symbol, the word Bluetooth with I think that's a copyright or registered trademark, and then the small word Blue Smart. Then that means that those devices have standard GATT. They adhere to the GATT standard for the type of product that they are. And you can go to the Bluetooth.com site or Bluetooth.org site and read about all the different standards and get the XML information about them, which will give you the UUID CAT class for each of the approved standards that they have. Basically, they reserve in the first long word, they reserve, I think they start with 1800 to 18FF. They reserve those first UUID values for the standards. So any custom ones will start at 1900 hex. All those are hex numbers. When you start doing the discovery, for example, the Wahoo Fitness Scale was, I think, 1901. And someone asked me along the way, what if you're in like a gym and everybody's got these heart rate monitors? How do you know which heart rate monitor is which? And the way to do that is you'll have to discover all the heart rate monitors you can find. And each heart rate monitor will have a serial number and a manufacturer string, and those are services and characteristics that you can get the values of. So, but what if I have a Polar H7 chest strap heart rate monitor. What if everybody's got Polar H7s? Well, then you have to go down to the serial number. Each one has a serial number. And maybe if you go into a gym or you're in a fitness center or something, people would register their chest straps, for example, to assign them the chest strap heart rate monitor and the manufacturer string and the serial number and maybe even version number. Those are some of the service characteristics from the manufacturer service that you can pull out. So that way you could find Al's heart rate monitor versus mine if we were standing next to each other, if you wanted to monitor who has the better or worse heart rate. But all that's doable with code. So.
Yeah, as you were talking, it reminds me of another common question I get is it possible to use this Bluetooth LE component with non-standard GATT profiles? All this time we've been talking about standard GATT profiles. And I recall not too long ago, David, you or Jim McKeith, you did a nice gadget and wearable webinar on, I think you used it on a Bluetooth car. That was a non-standard GATT profile. So without GATT support, you can still access the devices and the sensors and the gadgets. GATT does make it easier by defining how the interfaces work, but without GATT, you just need to create your own interfaces.
Yeah, it's a little bit harder. When it's GATT, you know which bits of which words, the data you get from the device, what they're defined as, because that's part of the standard for a specific characteristic. For example, you get the heart rate from X number of bits in one of the data words that comes back. What we ended up doing is we used the Explore Devices LE to find the Bluetooth LE devices, and then once we found it, we got the UUID so we could connect it, and then we would dump out the services, and some of them were non-standard services. So we said, well, what does that one do? And one of them didn't even have a string name. They just had a UUID. So we thought, well, maybe that's the data that we want. And then it had a characteristic that didn't have a name. It just had a UUID for the characteristic. So we looked at the data coming in and figured out which bits mattered and were associated. We also did this with a fitness scale. We did find the UUID. It was 1901 hex because we found it in a BlackBerry developer forum, which is kind of a strange thing, but we found it there. And then we were dumping out the data, and we said, wow, the good thing with the fitness scale is it had an LCD screen on it, so we could see the weight, that was transitioning until it got stable and it froze the value. And we could see that data coming in. There's attributes on Bluetooth LE. One of those is to be notified, and that'll just fire on characteristic read events as the data keeps coming in until it stops. And so we could watch that, and we saw the data coming in. And then when the scale stabilized, it displayed on the LCD the weight and also the letters SC, I guess for scale or stable weight. I don't know what it meant. We couldn't find the documentation. But we saw this bit go from 0 to 1, so we said, oh, when that changes from 0 to 1, that means that it's not sending any more characteristic notifications, and that the weight is stable. And then we found the data that was sort of changing a little bit as we put different weights on the scale. And then Jim figured out which were the bits, but then we were trying to make sense of what was on the LCD value related to the bits that we were seeing. And it was Jim McKeith that figured out that he had to swap the bytes, that the bytes were in reverse order. Maybe it saved some circuits or something. And that it was in hexagrams, or 1/6 of a gram. So, or hectograms, I guess, hectograms, not hexagrams, hectograms. And then from that, we could just multiply by a decimal number and get the exact weight. And the good thing was we could see the data on the LCD display of the scale, and then we could see the data coming in through the Bluetooth LE component. So sometimes if you have a device and it's GetCenter, it's great because it defines all the characteristics and all the characteristic value formats and the types of the characteristics. Is it floating point? Is it integer? Is it a date or whatever? That makes life easy for developers. The other thing is if you're thinking about a device that you need for an application solution, go to that manufacturer's site and see if they have either an API or a developer program. And if they have an API or a developer program, that might help you get more documentation, maybe some sample that you can sort of read through and get the information about the bits and so on. But yeah, if something is GATT standard, if it has that Bluetooth Smart logo on the box and the device, then your life is much simpler because it'll adhere for the type of product to the standard for that product. And that just makes life simpler.
Excellent.
Yeah. So,
and one of the other, when we're talking about these cloud-based solutions, these back-end as a service solutions, so for these applications, I use the Kinvey back-end as a service provider. So sometimes I get asked, are there any other types of back-end as a service provider you can use? Well, inside of XC7, in addition to supporting Kinvey, we also support Parse and App42. So now the process to use either of those is very similar. So in the IDE, you would still use the same backend query component, backend storage component, and backend push components, and then they would all get connected to the whatever backend service provider component you want to use, whether it's Convey, Parse, or App42.
And
The
all
only difference is each vendor, Convey, Parse, or App42, their web interfaces are a little bit differently, so you just need to get familiar with the web interface, but then you can do exactly the same thing we did with Convey. Let's say you did start with like Convey and you added those data collections and you were using JSON, so they all also support JSON. So you can take that same data collection that, let's say, I stored in Convey, and now you want to use it in Parse, so you could do that. You could export the JSON data out of the Convey and import it back into Parse or App42, and you would get the same column structure. I know internally at Embarcadero, we tested all three of them, Convey, Parse, and App42, and they all seem to work similarly the same.
Yeah, as far as the components for storage and user, there's all the BAS components. I should also mention that we also have a provider for our own enterprise mobility services, EMS server. So there's an EMS provider that allows you to use the EMS server that you could choose to deploy, in addition to the other cloud service providers that are supported. And again, there's also a base provider, a custom provider. So if you want to build your own backend as a service, your own custom provider, you can inherit from that base class and add your own support for whatever you might need to do in your solution space. So if there are any other questions, we're a little past the sort of hour-and-a-half time that we do, but it's been great having everybody here. There was a question about the source code to the samples, and Al, you said you would put those somewhere? Or
yeah, absolutely. So I suspect when you're going to upload this to the site, we'll attach links to get to the source code of all the examples and that detailed white paper that we put together, showing you how to build these applications from scratch.
Yep. So yeah, in the RAD in Action, if you just search RAD in Action, there's a RAD in Action landing page which has all the previous RAD in Actions with a little button that says Learn More. And so you can go there, and when we're finished today and get all the little bits and pieces together, there'll be a landing page for this Connected Apps RAD in Action that has a nice page and a picture of Al, and it'll have the link to source code and documents. And what I'll probably do, Al, is I'll extract a couple small video snippets for people that go there, want to just check a little bit out, and then there'll be the on-demand replay. Yeah.
Yes.
Okay, Al and everybody, thank you very much for joining us for Building Connected Apps. You can connect and leverage all the technology you have today in your VCL and Windows apps or in your multi-device applications. You can take advantage of connecting them all together through network and through Bluetooth, as well as integrating all these cool devices. Either now or in the future, you've got all of that in EXE 7. And again, check out the RAD offer page to see what's happening. If you need to test the iOS 64-bit, we have a test going on for people that need iOS 64, so you can go to JT or John Thomas's blog or just search iOS 64 beta on the internet. You'll get to that information. There's an email address. I think it's iOS 64 beta at embarcadero.com. But anyway.
Oh, when you just mentioned JT, it reminded me, if you haven't seen it yet, in this month's Venture Beat article, JT, our Senior Director of App Development in Embarcadero, he discusses what the Internet of Things means for business app developers. So you haven't seen it yet, find that, or we'll send a link for it and read up on it, and you'll hear from John Thomas, JT, what he thinks the Internet of Things means for us, for developing these business app, business app developers. So that's quite exciting.
Alf asked a question about distance. I know classic Bluetooth versus Bluetooth LE, separate from environmental issues, steel walls, whatever it might be. I think you pointed to an article from the Bluetooth.com, the Bluetooth organization page.
That's correct. So yes,
it's thought 100 meters for Bluetooth Classic, approximately 300 feet, whatever that is.
Yeah, so yeah, we subscribe. So whatever the spec device has as far as Bluetooth LE or Bluetooth Classic range, and that's what we're going to respect, and that's what we're going to use. So, and it's all based on the GAP specifications for these devices,
And it's
and it's all described on that Bluetooth
transmitter power.
website.
And it's the transmitter power of the devices as well.
That's also true. And that brings up that great, there's a great sample we ship with, proximity, where you can see, it'll actually give you the, it'll scan a room or scan an area looking for all Bluetooth, LE or Bluetooth Classic devices, and it'll tell you your proximity to it, and it'll gauge the strength of the signal. So that's a great little sample app we ship with. If you want to see and find all of the available Bluetooth devices in your area and get a proximity range of where they are and its single signal strength.
Yeah, and then there was a comment about some of these different heart rate monitors. I have the Polar H7. You have the Zephyr heart rate monitor. Both of them are chest straps. There are other kinds. There's things for your finger, earlobe, foot, and so on. If you look at the enumeration for the Bluetooth LE and the sample code for the heart rate sample that we ship, you'll see the values that come from the GATT standard for the location or position of the monitor, and that's burned into the hardware devices themselves. And Alpha was mentioning that some of these aren't as accurate, and that probably if you're doing analysis, you should do some kind of smoothing, averaging, or whatever over a period of time than taking very precise instantaneous measurements.
Yeah, Alf makes a great point there, right? So the data coming out of these things is only as accurate as the data it can produce. For the example I use, I took my heart rate monitor and I had it attached to my chest using a strap. But when I'm on the road, showing this to customers and at webinars, I don't have the luxury of strapping this device to my chest. So, for the devices I use, I can take any two fingers. It could be two fingers on the same hand or thumbs and touch its contacts, and that device will start sending data. Is it my true accurate heart rate beats per minute? Probably not, but so Ralph does bring up a good point. It's great to say what he did there. It's probably better to do a floating average of the data to get a more accurate measurement of the true data that's coming from the devices.
Yeah, and then you were connecting to a backend service, in this case Convey, but it could have been Parse, App42, or some other backend service. How to think about the user management? And I know Serena's done a blog post about user management for her backend as a service series of blog posts, and we use like sample users. We create some users, but you should build into your application, right, Al, where the user would log in and you'd create a user. I think Serena, one of her blog posts showed about user management, creating users in the backend cloud, right?
Yeah, that's correct. So for this example, we use Kinvey. The other two providers we provide out of the box with XE7 is Parse and App42. And then the process to use any of those other BAS providers is similar. So likewise, in the IDE, you're going to use the same backend query component, backend storage component, backend push component, and they all get connected to the whatever BAS provider component you use, whether it's Kinvey, Parse, or App42. But so in this example, I use Kinvey, but you could do the same with the App42 component or the Parse component. And the only difference is for these backend services, backends, is their web interfaces. So you just need to become familiar with their web interface, and then you can do the same thing that I did with Kinvey. So they all support JSON. So for example, if you had to create a data collection like we did, and I stored it in Kinvey, and for some reason you now wanted to move it from Kinvey over to Parse, and Parse supported JSON, then you can simply export out that JSON data from Kinvey and import it back into Parse, and you're going to get the same column structure. So internally at Embarcadero, we tested all three of these, Kinvey, Parse, and App42, and they all seem to work just fine and just well.
And they have different pricing plans for number of users and or number of devices. Different backend services have pricing plans based on different methods. Some of it's API calls, some of it's users, some of it's devices. So you should check with each of those providers and their pricing plans, and also their service level agreements, their security agreements, which ties us into the next question, I think, and you had the links to it about what each of these kind of providers provide as far as security, but there's also questions about what about the security between the device and your application itself, separate from going to the cloud. Any advice there, Al?
That's a great question, because I know, so let's see, we're looking at, I know like for these apps that we spoke about, we're talking about medical apps or financial apps, so anytime you're dealing with those types of apps, you always get involved with HIPAA and security requirements. So if you're going to use a back-end as a service cloud provider, my understanding is that they do encrypt the data as it's going across the wire and getting stored into their cloud. Bluetooth LE itself also provides strong security, AES 256-bit encryption for strong encryption and authentication of the data packets as it's going across the wire. For each of these providers, Kinvey, Parse, App42, if you visit their sites on security and HIPAA compliance, they will spell out what their level of compliance is for security of storing the data, and if or not they are HIPAA compliant. Now, HIPAA, when you're dealing with something called HIPAA, it's more of a compliance thing, and it depends on whether you can audit. You can audit what's going on. Like I know for Kinvey, for example, if you want the application to be HIPAA compliant, they sell a business edition of their Kinvey, and that requires you to use a secure data link into a firewalled server to get their HIPAA compliance. A lot of times when you're dealing with the HIPAA folks, they don't like you to be sending this data to the cloud. They like this to be held internally on-premise in a firewalled server on your site. So once again, when it comes to security and HIPAA compliance, especially for these medical and financial apps, you need to look at the components that are involved just to make sure they do adhere to HIPAA and they have the correct strong 256-bit encryption. No, so one way we did it right now was to store the data in a cloud solution. Now, Embarcadero also has a database called Interbase. That's a great solution where you can store the data. So with Interbase, you could either store the database embedded onto the device, or you can take that Interbase database and you can remotely store it in the cloud. So Interbase also allows over-the-wire encryption. So as the data is moving from device over the internet into the cloud, that data is also secure in that transmission, and once the data gets into the database, it's also strongly encrypted 256-bit encryption. So that's an option you can use. And with Interbase, we include the Interbase Developers Edition, so you can try it. There's the Interbase Lite version that doesn't have encryption, but you can test what you're trying to do, and if it works, great. Then you can switch from the Interbase Lite without encryption to the Interbase To Go edition. Same file, same everything, just give you a different license key that now allows you to encrypt the data to keep it secure and safe both on the device, iOS, Android, Windows, Mac, and also remotely. So that's also an option you can use.
And then in the app tethering world, where you're just going app to app, for example, on a network or Bluetooth, we don't do anything special for the packets going back and forth, but you can intercept and encrypt, before you send and after, and when you receive, you could call whatever crypto libraries you want to call to encrypt the data before you send it over or receive it back through app tethering. There's no special hook in the app tethering components themselves. But again, you have full access to the data, the content, and do whatever you want with it on both ends.
That's correct. So I did use that method, send string. There's also a send stream.
Yep.
That will send values between the two. And as David mentioned, before you're sending that, you can encrypt it on the client side and then decrypted on the server side before it gets sent over the wire.
Yeah, I'd use send stream if I was encrypting stuff. That just makes more sense than sort of encrypting.
That's correct. Yeah. So the example I showed here, when we created the resource, we made it its type was of data, meaning we were sending data back and forth. The other type that I didn't show was stream. So when you create that resource, in my case I called it my BPM, my beats per minute. It was a data type of data. The other option there was for stream. So if you wanted to send images or pictures, or as David mentioned, if you're going to encrypt the data, then you would send it back and forth as a stream.
And then there was a question about could you have multiple app tethering things going on in one or more applications? That was a question that came up, Al.
Correct. So a lot of times the question is with app tethering. So we mentioned the two ways you can use app tethering with the allowed adapters. So you have the option of either using it over network Wi-Fi or over Bluetooth. And as I mentioned, if you wanted the two apps to communicate to each other, both of them either had to be talking network Wi-Fi or they both had to be talking Bluetooth. So the convention is you drop one tether manager on the form, and then you can have one or more profiles on the form. But in the case of, let's say I want the app to either support both network, Wi-Fi, and Bluetooth, I have not tried this myself, but it looks like it's possible to drop two or more managers onto a form and multiple profiles, and one of those managers could be using network Wi-Fi, and another manager could be using Bluetooth Classic. And then depending on how you want to connect the two to each other, I see it's possible. I haven't tested it myself, but I'm going to do this after this just to verify that's going to work. And that'll give you an option of either using network or Bluetooth app tethering from the same app. So that'll be pretty cool to try and test to see if that works.
And even though you set one of the types, Bluetooth or network, at design time, you could also write code that would use a tether manager and maybe for a while set that property to network and do a discovery and know that you're in there, and then shut it off, and then change it to Bluetooth, do a discovery, run for a while. So you have all those possible combinations that you can mix and match with. Yeah.
That's correct, right? That allowed adapters property is simply a property on the tethering manager. So in code, you can switch it in code if need be.
Yeah, there was. Go ahead, Al.
Nope, that was it.
Yeah, anything that we showed, obviously in code and at design time, you can, as you can do that stuff. There was a question about the Interbase to Go license. Its number of users or number of connections that you purchase in blocks 1, 5, 10, 50, 100, unlimited. You can find the licensing pricing information on the Interbase website and on the shop sites and through our reselling partners. So you have all
That's
of
right. And then I believe if you want to become a VAR or a reseller, then that becomes more of a business discussion, and then the license price per instance is based on the application you're producing and the price of that app. So that everything changes if you become a reseller or a value added partner or a reseller.
Yeah,
so two ways to do it, right? There's the shop price on what it goes for individual user, or if you want to become a VAR or a reseller, then that becomes a separate licensing discussion with the account manager.
And that's for all the editions, whether it's the desktop edition, the server edition, the to-go edition. IB Lite is free deploy on all 4 platforms. It just has the restriction on 100 megabyte database size, no encryption, and only 1 transaction active at a time.
All right. So thank you all for attending, and everyone have a great day.
Okay. Bye.